Okay, we're continuing our discussion of rate laws and talking about the steady state approximation today. In the previous video, I showed you this consecutive elementary reaction mechanism. A goes to I goes to P. We can write associated rate expressions for each of these elementary steps. They look like this. The question is, how do we solve it without taking a DiffEq class? And here's sort of the starting point. What if we assume that the concentration of intermediates was small? And because of that, the change in concentration is negligible. Change in concentration is negligible. That means it's about equal to 0, right? In other words, di dt equals 0. This has a name called the steady state approximation. It basically says that the rate at which intermediates come in and the rate at which they come out are constant, and so the concentration of intermediate doesn't change with time. That's what we mean by steady state. And it turns out this is immensely useful. Let me show you. For the first expression, dA dt, this is just a simple first order expression. We can integrate it. If I do that, I get something like A equals A naught e to the minus K1t. You know how to do that. If I apply the steady state approximation to the intermediate, I can say that this is approximately equal to 0. In which case, the concentration of I is equal to K1, K2 times the concentration of A. I take that, I plug it in, A0, K1, K2, e to the minus K1t, and I could now integrate it. Dot, dot, dot. This is a simple exponential expression. I could integrate it. I take this expression and I add it in here, equals K2, K1, K2 times the concentration of A, cancel, cancel, equals K1 A naught e to the minus K1t. Again, a simple exponential expression. I could integrate it and get some result. Okay. I'm not going to do that in this video. I'm simply going to show you the result, which is here. Okay. If I integrate each of those expressions, this is what you get. And I want to compare that to the full solution, the analytic solution that you would get if you applied your DiffEq classes. And I want to do a little math problem, which is under what mathematical conditions does the steady state approximation approach the full analytical solution? And if you look at this, what you might start to recognize is that, well, if K2 is a lot bigger than K1, this e to the negative K2 is going to disappear more quickly. K2 minus K1 is going to approach K2, and you get this result. Trust me that the same thing will end up being true down here. What I hope you might be able to see is that the steady state approximation approaches the full solution if K2 is much, much bigger than K1. In other words, if the reactions in which intermediate species are consumed are much faster than they are produced. Or in other words, if the mechanism has a rate determining step. Okay? The steady state approximation works well if a mechanism has a rate determining step. Again, this sometimes leads to some questions for students. If it only works for things which have a rate determining step, why use it at all? Right? Sometimes people say, if it's not that different than the full solution, why use it? Right? I don't see the benefit of it. And let me tell you, in practice, reactions with intermediates are often fast. That's why it's an intermediate. If it was not fast, if it was slow and stable, it would be a product or a reactant. Furthermore, the probability that all of the steps in a mechanism are similar is really low. There is almost always a rate determining step. What's more relevant, however, is that if I have more complex mechanisms, the steady state allows us to make predictions for multi-step mechanisms. If it's not just A to I to P, but it gets more complicated, the steady state approximation becomes extremely useful. And the problem I'm going to solve is here. So here's a reaction. Here's a proposed mechanism. These are the steps that we use to do it. Identify the intermediates and the component of interest. Use the steady state approximation to solve for the concentration of intermediates. Plug in and derive a simple rate law. Right. I'm going to work through this problem in a separate video. It's up on the good old-fashioned worksheets. So if you want to look at that and follow along, that'd be great. And I will show you that solution in the next video.